Okay, let's start today's seminar. Today's seminar speaker is Professor Torsten Bringmann from University of Oslo, and he will talk about precise dark matter relic abundance in decoupled sectors. So please start.
Yeah, okay, so thank you very much. Thanks a lot for the invitation. I would love to be there physically, but well, online is almost as good. Okay, I guess I don't have to convince you of the fact that there is dark matter around and there's overwhelming evidence on all scales. Yeah, so ranging from galactic scales to cluster scales to the larger scales that we can observe. And the whole point is, of course, that this is sort of independent evidence. Yeah, but I've noticed that when I talk to people that aren't that familiar with dark matter, this is sort of almost frightening and seems like it's very complicated physics that's entering here. So I think a nice argument is that cosmology without dark matter really fails already at the linear level. Yeah, so it's only linear gravity that we need at input, so no fancy GR effects. And the only thing that we need to know is that a baryonic component or ordinary matter, non-relativistic matter, any perturbations in this component would grow linearly with a scale factor. And then it's just a matter of observations. So we know the radiation density today, we know the CMB temperature. Sorry, we know the CMB temperature and we know the perturbations at the time of the CMB. Yeah, and then just extrapolating from these initial perturbations at the time of the CMB, we would see that, okay, so there's something missing. We would see that the perturbations today would only be at the level of 10 to the minus 2. Yeah, so that means that we would still be in the linear regime. We wouldn't have any structures whatsoever. So basically to convince yourself that we need dark matter is just looking out of the window. Okay, but of course, we can do the full analysis and do precision cosmology. And then you all know that dark matter indeed is confirmed to be a crucial ingredient. And this striking thing is that we can really describe it with a single parameter. Yeah, so it's only one number that gives this nice fit to all the data. And we can determine this number to a % accuracy. Yeah, so you can, for example, choose it as the measured dark matter density today, so the co-moving number density. And the only thing that enters then is that we assume that there's really nothing but gravitational interactions. It's cold, no dissipation, and that the energy density is co-movingly conserved. Now, of course, you can question all of these assumptions. So I just want to mention that one of the things that that can change is, of course, or that you can vary, is this assumption of the co-moving energy to be constant. Yeah, and this is actually well motivated. So dark matter could be decaying. You could have late time annihilation. If dark matter is made of primordial black holes, you know that a significant fraction of the rest mass is converted to energy, namely gravitational waves. And you can just ask in a sort of model independent way, if you change this assumption here, yeah, how well do we know that dark matter exists? And then the answer is that the accuracy to which you can determine the present abundance is still at the level of 10%. Yeah? So it's not the % level accuracy that is typically claimed, but it's still 10% as long as the conversion takes place during matter domination. And of course, if conversion takes place early in the radiation dominated phase, a much larger fraction can be converted because the dark matter component is so subdominant with respect to the dominant radiation component. Okay, so if we know that dark matter exists, this also means that we basically have evidence for physics beyond the standard model. And we also know what it is not, but obviously this is not good enough to fix what it is. Yeah, so I just want to start sort of this talk with a little reflection about why we consider the kind of models that I want to focus on, namely dark sector models. So this is why I'm trying to put things a bit into context here. Yeah? And you know that there are many candidates, and the whole point is that we really don't have any clue. Yeah? So just from the cosmological observation point of view, It could be anything like many orders of magnitude in terms of the interaction strength, many orders in terms of magnitude, many orders of magnitude in terms of the dark matter mass. Yeah. Now, of course, you've all heard about weakly interacting massive particles, and this is basically the paradigm that I will start from and then modify. So let's just briefly recall this. The main point is, well, the first point is that these are candidates that are well motivated from particle physics. Yeah, so basically motivated from fine-tuning or hierarchy problems in the standard model, extensions to the standard model that have an independent motivation from the dark matter problem. And then people noted early that if you study the thermal evolution of such particles in the early universe, this is something that is described by the Boltzmann equation. So the left-hand side basically just shows how the number density of these particles evolves in an expanding universe. So this is the time derivative of the co-moving number density, which is plotted here. And the right-hand side makes sure that as long as these interactions are strong, as long as this term is large, then you basically force this to be to follow the attractor solution, namely the dark matter density of the dark matter particles, the density of the dark matter particles following the equilibrium density, which is this curve here. Yeah, but then at some point, this interaction rate will fall behind the Hubble rate, and the number density, the co-moving number density, freezes out, which means that the right-hand side is essentially zero. So then again, the co-moving number density is just conserved. Now, if you solve this numerically, you find this relation here. Yeah, just this is, I mean, of course, as you increase the annihilation rate, you will stay in equilibrium longer, and therefore the abundance will go down. This is not unexpected, but what is kind of surprising is the scale that appears here. So it so happens that for weak scale interactions, we just get the observed abundance. And that, of course, has been discussed and coined the WIMP miracle, and is one of the major motivations to consider weakly interacting massive particles as dark matter candidates. Now I should mention that, of course, this interaction strength, this is a very clear prediction and can, in a model-dependent way, be translated to expected detection rates in various experiments. But we haven't seen any of these dark matter particles. So that means that this whole idea, this scenario is seriously pressured, sometimes even called dead, which is not true. WIMPs are perfectly alive, but it's certainly correct to say that it's pressured. So this is one of the motivations to consider the kind of models that I will focus on here. So the idea is that this is the standard model. So it's governed by gauge interactions that you're all familiar with, and then we have the standard model particles. But then there's nothing that forbids the existence of a dark sector. So some particles, which I call dark matter, there could be dark radiation, there could be other particles that are neutral under the gauge group of the standard model. There could be some additional gauge groups that only these particles are charged under. So they really don't talk to each other at all. So when I say that they don't talk to each other at all, this is not quite true, because typically, if the same kind of thing happens here, so for example, if the gauge groups are spontaneously broken, then you will also have a dark Higgs field. So then basically you cannot avoid such a Higgs portal coupling, because you have a dimension 4 operator that connects the two Higgs fields. Correspondingly, there could also be kinetic mixing terms. So there are various portals that generically ensure that the standard model, so the visible sector and the dark sector, thermalize at high temperatures. So as a consequence, you can then still have relatively large gauge interactions within the dark sector without being in conflict with experimental searches for dark matter. So that means that once these two sectors decouple, because this portal is not active anymore, then entropy is conserved separately in the standard model sector, in the visible sector, and in the dark sector. So that means generically in these models, that the photon temperature, so the visible sector temperature, is not the same as the dark sector temperature. But not only that, you can actually compute the dark sector temperature. Yeah, since entropy is conserved separately, or at least if you have large enough gauge couplings here to thermalize the dark sector, then entropy is conserved separately, meaning that the evolution of the temperature is really just a matter of how the degrees of freedom evolve. Yeah, so it's totally defined by the particle content in the standard model, in the dark sector and in the standard model, as well as the decoupling temperature due to the portal interaction. So these are very predictive scenarios. Yeah, and this is indeed one of the main motivation to consider these kind of scenarios if we don't know what dark matter could be, because we have a predictive, a high predictivity in terms of the cosmological evolution, and because we have a thermal production mechanism, and that's what I will be focusing on. Yeah, so we can exactly predict the dark matter relic density and use that to constrain dark sector couplings. From the sort of guiding principle or philosophical point of view, it's a rather opposite approach to the WIMP dark matter paradigm. Yeah, so rather than trying to find some top-down hierarchy arguments to motivate model building, here it's rather simplicity. Yeah? So we add to the standard model just a simple minimal addition, so like one additional gauge group without going beyond any of the well-established concepts. So we're just using Young-Mills theories, spontaneous symmetry breaking, nothing else. Then of course, you should ask about testability. Yeah? So a good physical theory should be testable. And unlike for WIMPs, these kind of models will have no signs in traditional searches for dark matter. You wouldn't see them in indirect searches, you wouldn't see them typically in direct searches, nor could you produce these particles at colliders. Yeah, of course, I mean, the portal interactions make sure that there's some interaction, so this comes with a grain of salt, but in principle, you can also turn this argument around and say this is actually an advantage in that we haven't seen WIMPs. So this kind of model building is a way to evade the stronger and stronger constraints from traditional searches. Yeah, and on the other hand, the absence of signatures in traditional searches doesn't mean that you can't test these models at all. Yeah, in fact, there are many observables, very relevant observables related to cosmology. Yeah, so the dark matter density, of course, that's what I will focus on here because of the thermal production. But these kind of models can also have an imprint on the power spectrum of matter density perturbations. Yeah, I will briefly mention that. You could, for example, see a cutoff in the power spectrum that you can see, that you could observe with the observations of the Lyman alpha forest. There could be a contribution to from dark radiation to the effective number of relativistic degrees of freedom. Yeah, so there are cosmological effects. I haven't even mentioned self-interactions here. That means that you just have a different type of observables to look for. And indeed, you could connect these two reported anomalies at small scales, notably in cosmology. And this is, of course, one of the main motivations and practice why people have started to look at these models. So one way of putting this is that, well, WIMPs were certainly a good way, a good possibility to start looking. Yeah, but it's this kind of argument that you should look where you can look, where you can expect to find something. And I'm just trying to say that these kind of models actually do provide another lamppost, and that there are many observables related to them. So if we haven't seen anything here, why not look there as a next step? Okay, so in that context, I should mention DarkSUSY. Yeah, so this is a numerical package to compute all dark matter, all kinds of dark matter observables. Yeah, and since version 6, so some 2 years old now, the name DarkSUSY here is in some sense just historical. So it's by no means restricted to supersymmetric models anymore. We have separated a main library that is essentially independent of the particle physics properties, and then you can link the particle physics module to this to perform your calculation. Yeah, and in particular, in recent development, there's been a strong focus on general dark sector observables of the type that I will be talking about here. Yeah, so for example, it's fully implemented now that the dark sector temperature can be different from the photon temperature when you perform relic density calculations, but also kinetic decoupling, with a model-specific, model self-consistent evolution of the dark sector temperature. Self-interactions are implemented. The contributions to delta and F from a given model is implemented, and so on. Okay, so let's then take a look at the standard treatment, the standard way, of getting to this equation and then solving it. This is important because you can make precision predictions for the observed dark matter density today. But of course, it's also important because it kind of fixes the interaction strength. This is the standard plot that you've all often seen, where the average annihilation rate at the time of freeze out is plotted against the mass of the dark matter particle. So this is a very generic result, and the reason this varies here is just because of the variation of the standard model degrees of freedom, light degrees of freedom in the early universe. So basically, at high masses, we have freeze out very early. So then the number of degrees of freedom in the standard model is much larger, and therefore the Hubble rate larger than at later times after the QCD phase transition, when the number of degrees of freedom has dropped dramatically. So the other point, apart from predictivity of such a plot, is that this kind of benchmarks the experimental searches. Because saying that we have a thermal production mechanism fixes the coupling strength, fixes the relevant interaction strength that experiments should look for. So that's the real reason why these kind of plots are so important. And of course, if you think even of global fits, of parameter fits, then on top of that, you know that the relic density or the dark matter density today is determined to a high precision, percent level precision. So that means in the total likelihood driving global fits, the relic density plays a crucial role. It really cuts out small slices of the parameter space. So the motivation, this is well studied in the standard scenario. And I think this provides good enough motivation to try to achieve the same level of accuracy also in these kind of dark sector models. Okay, so let's briefly go through the standard case again. Of course, there's a nice simple equation, but you also know that if you have nice and simple equations, there are always assumptions that enter. So this equation that we've seen on the previous slide is based on this fundamental Boltzmann equation at the phase space level, and you get it by just integrating over all the momenta. So on the left-hand side, we've just the Liouville operator, so this describes the expansion of the universe. And on the right-hand side, we have the interaction term, and the dominant interactions that we should worry about are annihilation and creation processes of dark matter and scattering with standard model particles in this case. In the standard case, and the standard model particles would be replaced with dark sector particles in the cases that I will discuss here. So what are the main assumptions that enter in the standard form of the Boltzmann equation? The first assumption is that dark matter becomes non-relativistic while it is still in full equilibrium. So that means that in this equilibrium distribution, and therefore in the equilibrium number density that we've seen in the previous equation, we use that we have a Maxwell-Boltzmann distribution for the dark matter particles. And that means in particular that we can, because it is very small, we can always neglect quantum statistics of any kind. The second main assumption is that dark matter remains in kinetic equilibrium. That means that even as we freeze out, as we depart from full equilibrium, we can still write the phase space distribution in this form. So we just pick up a chemical potential, but from the point of view of solving the equation, it means that we just have a temperature dependent, not energy dependent prefactor in front of the equilibrium distribution. This is a crucial assumption leading to the standard formulation for the Boltzmann equation of the number density. And finally, and this will also turn out to be important for today's discussion, the assumption is that the standard model particles never build up significant chemical potentials. Yeah, and that means that, well, because of energy conservation in these processes here, it means that effectively what enters for the standard model particle distribution is also a Maxwellian distribution. Yeah. So why can we be so sure about this? Well, because we know the standard model interactions. Yeah, so all the particles in the standard model in the heat bath are coupled so tightly to each other that they simply cannot build up any significant chemical potential. So for the standard model evolution, this is an extremely good assumption. Okay, so let's look at how this works out for the dark sector. And for concreteness, let us just look at a simple phenomenological setup. So we consider a fermionic dark matter candidate and just a scalar, an additional scalar in the dark sector, such that the freeze out in the dark sector is driven by dark matter annihilation to these scalars. Yeah, and we will keep the number of degrees of freedom of the scalar as a free parameter just to show the impact of this. It can, of course, I mean, phenomenologically, this wouldn't change if it's, for example, a vector. We also assume for concreteness that the decoupling, yeah, so the portal ceases to be effective at a very high temperature. And I've shown you before the way the temperature in the dark sector evolves as a function of the standard model temperature. And you see that the only thing that entered there were the number of degrees of freedom. So as long as we have a decoupling temperature that is higher than all of the masses that are involved, this basically converges to a well-defined and unique scenario. Okay, so then we will discuss two cases, and they are quite different in that the first case, we consider massless particles, massless scalar particles, in which case the chemical potential is also would always vanish, just like in the standard model case. You know, the second case that we will discuss will be the case of massive scalars, annihilation products, where this is not so clearly satisfied, or it's a model-dependent question whether it's satisfied or not. Yeah, so why is it not a model-dependent question for massless scalars? Because, like, even if you try to write down the most minimal Lagrangian, you can never avoid these kind of processes. Yeah, so you have infrared enhanced production of low energy scalars of this way, and this is something that you cannot avoid. So you will always have number violating interactions for the scalar. Okay, but what does that mean? As long as we are in kinetic equilibrium, it means that we can really, it's exactly the, like in the standard model case, we just have to be careful to use the dark sector temperature rather than the heat bath temperature, the standard model temperature at all relevant places. So concretely, this means that we should use the dark sector temperature in the thermal average. We should use it in the number density. And of course, it also enters implicitly in the effective number of degrees of freedom, because if we have relativistic degrees of freedom in the dark sector that are much colder than the standard model, then these are, of course, suppressed. And I mean, this is in principle straightforward, but also it's like looking at the literature, usually at least one of these things is not fully consistently implemented. And the other main motivation for why we wanted to do this, and to just be very explicit and rigorous about this, is that we've never seen the corresponding plot that I've shown you here for the standard model that you've seen on the previous slide for dark sector calculations. Yeah, so what happens? Yeah, this again is the standard model plot. And by the way, if you do this as a precision calculation, there's also a slight difference between Majorana and Dirac particle. You often find the statement that Dirac particles just, so I mean, of course, for Dirac particles, you have dark matter particles and anti-dark matter particles, and you often find the statement that you need exactly twice as large interaction strength, because you need to produce both of them independently. But you see there's actually a small difference that relates to the exact time of freeze out. Okay, so what happens in the in the case of dark sector calculations, you see that the corresponding curves can be quite different. So the top two curves are for the simplest case that the scalar has only 1 degree of freedom. And if you have more degrees of freedom, you get to these curves here. So it's indeed relatively straightforward to understand the form of these curves by just recalling our relation that I showed previously for the temperature ratio. So the question is just what happens at the point of freeze out, whether this temperature ratio is larger than 1 or not. And you see that if it's exactly equal to 1, this is when these curves cross the standard model case. So to the right, we have a larger dark sector temperature than visible sector temperature. And that is because in the standard model, this is for large dark matter masses, so high freeze out temperatures. So in the standard model, the change in the number of degrees of freedom was not so significant yet. So the standard model heating, or the heating of the standard model sector, is less efficient than the heating in the dark sector. Because in the dark sector, we have already something happening, namely relativistic initial dark matter particles becoming non-relativistic and thereby heating up the dark sector and the temperature of these S particles. And to the left, it's exactly the other way around. Here, the heating in the standard model is much more efficient because during the QCD phase transitions, many degrees of freedom are lost. So what is the effect then? Well, if the dark sector is hotter than you would expect in the corresponding standard model calculation, then it's in particular the number density that is higher at any given reference time or reference standard model temperature. And in order to get down to the observed relic density, you need to increase the annihilation rate. So that is why all these curves are higher and all these curves are lower than the standard model case. Okay, of course you can ask, why would we consider a constant annihilation rate? And the implementation in DarkSUSY just allows any arbitrary matrix element. So for example, if you've ever wondered how these curves would look like for P-wave annihilation, this is how it looks like. And it's also relatively straightforward to understand the difference to the previous plot that I showed you. We can also look at a like more complex example, where we have a Dirac dark matter particle coupled to a vector mediator, a massive vector mediator from a spontaneously broken U1, for example. And this vector mediator coupling again to some light degrees of freedom in the dark sector. So this is a model that has been studied quite extensively in the literature, and it's motivated for multiple reasons. So I don't have the time to go through all of them here. I just want to connect it to the observables that I mentioned previously. So indeed, you can arrange parameters in this model such that you do not only get thermal freeze out and can predict the dark matter relic density, but you can also achieve late kinetic decoupling, because elastic scattering with these dark radiation particles is so efficient that you get late kinetic decoupling and therefore a suppression of the dark matter, of the power spectrum of matter density perturbations, and thereby potentially address the missing satellite problem. You can arrange for dark matter self-interactions, because this coupling strength here of the dark matter particles for themselves by exchanging the mediator is very efficient. So you can address things like the cusp versus core problem, or the too big to fail problem. And you can also address in these kind of models the H0, the Hubble tension. So the main point is that this is the prototype of a model that falls into this category of being testable, not by traditional dark matter searches, but by cosmology. So let's just show this explicitly. So if we have this kind of model, then we basically have three parameters. We have the dark matter mass, the mediator mass, and we assume the dark radiation to be essentially massless, and then there's the coupling. This coupling here is fixed by the relic density. This process is much more important than this one in setting the relic density. So here we also have Sommerfeld enhancement, which is fully included in the current implementation of DarkSUSY. We can use the photon, the dark matter temperature evolution, as I explained before. It's uniquely fixed by demanding that decoupling is happening at very high temperatures. So then the whole parameter space can basically be plotted in just this 2D plane. And then once we've done that, we can connect it to the observables that I've mentioned before. So for this self-consistent relic density calculation, we can, for example, ask what is the cutoff in the power spectrum of matter density perturbations induced by these scatterings. Yeah, so I can just draw isocontours, and like to the left of this green line, the suppression is so significant that we wouldn't form any dwarf galaxies. So this is very clearly excluded observationally. To the right, we have no observational handle yet. And somewhere in this green band, you can hope to address the missing satellite problem if you believe there is a problem. In the same way, we can calculate the self-interaction rate. Yeah, this is also something that is implemented in DarkSUSY. And the same goes here, like everything to the left and below this blue curve here is very clearly excluded by observations. And if you believe that there are actually problems in the standard, in the cosmological standard model that need to be addressed, then these are the kind of interaction strength of about 1 centimeter squared per gram that you need to have in order to address these small scale problems. Yeah, so either way, this is a predictive model, in that there's a large region of a complete dark sector model that is really testable and ruled out by observations. Yeah, and potentially you can even address anomalies. And like in this region here, you could address all of these 3 anomalies at the same time. Okay, so I should just mention that, I mean, this is really simple and straightforward to use, and there's even examples. So if you decide to download DarkSUSY, you can even change the model here and explore your own phenomenological models and reproduce these kind of plots for essentially any dark sector setup. Okay, so let's go to the second case. This is like less trivial, and that is this situation where the annihilation products actually build up chemical potentials. So if we don't have massless particles, massless scalars, then this cannot in general be prevented, unless, of course, we add new physics, additional assumptions. For example, some massless states in the Lagrangian that the S particles can annihilate or decay to. Yeah, that would ensure a vanishing chemical potential. But if these particles do build up a chemical potential because there are no other states that they can decay into, then it means that none of the basic assumptions that we made for deriving the standard Boltzmann equation are satisfied anymore. Yeah, so even when we assume kinetic equilibrium, these particles will not follow a Maxwellian distribution without a chemical potential. Yeah, it means also that the dark matter distribution cannot be described in this way anymore in equilibrium, nor can it be described in this way at freeze out. So in particular, I mean, the one thing that we can still use, however, is that if we assume kinetic equilibrium, and of course this is something that can be tested in a given model. So if, in other words, the scalar particles, the S particles, still scatter efficiently, elastically with dark matter particles, then it means that all the particles are kept in local thermal equilibrium, maybe not in chemical equilibrium, but in local thermal equilibrium. So it means that all of the particles will follow a Bose-Einstein or Fermi-Dirac distribution. Yeah, and what you have to do in that case is to really use that distribution, including the full spin statistics. And then basically you have a system of equations that you need to solve. So the 3 parameters are the dark sector temperature. Yeah, so I just denote it as T chi because it's the same, assuming kinetic equilibrium, it's the same for all the dark sector particles. And then the two chemical potentials that we have. So it's 3 parameters. And in practice, the way we do this is to look basically at the equations for the number density. So one equation for the dark matter particles. The IA here is in principle taking into account that there are both dark matter particles and anti-dark matter particles if we have direct dark matter, and then the number density for the scalars. And on top of that, we only use energy conservation. So in particular, we also don't have to assume explicitly entropy conservation, though in practice, entropy is conserved to relative good precision for the parameter points that I will show you later. And then, like these 3 equations here, you can transform into a set of coupled differential equations for the 3 parameters that we're interested in by just taking the total differentials. Okay, so how does that look like? Well, here I just plot the evolution of the abundance, so the number density of the respective particles divided by the entropy, so essentially the co-moving number density as a function of time, so that's a dimensionless parameter here. And the solid lines show always the abundance of the dark matter particles, and the dashed lines the case of the scalar S particles. So as expected, the abundance of S increases. Well, why is that? Because the S particles basically don't have any option to get rid of their chemical potential. Yeah, so the dark matter particles annihilate into the S particles, and the S particles cannot decay away. Yeah, so in particular, before kinetic decoupling, yeah, so I indicate this with the vertical blue lines here. This is chemical decoupling roughly. So at earlier times, S and chi are in chemical equilibrium. Yeah, and then in chemical equilibrium, we know that the chemical potentials must be all the same of the particles. So that means as the dark matter particles start to build up a chemical potential, the S particles also have to build up a chemical potential. So if we compare this to the case of, to the standard case, if you would just naively use the standard Boltzmann equation, assuming that chi is coupled to a heat bath, yeah, with no chemical potential, then you would get these dotted lines. So the difference is most striking if we have a mass difference between chi and S that is very small. Yeah, so here we have an almost degenerate scenario, and the abundance that we get for a given coupling, so in this plot, all the couplings are the same. For a given coupling, then the abundance is much higher. So why is that? Well, simply because the number density of the particles, of the S particles, is much higher than in the standard case. So that means that the interaction rate is larger. Yeah, and therefore, yeah, so, okay, good. So, but then, like, if we have a higher abundance here, it means that we need a larger interaction rate to bring the abundance down to the relic abundance. Yeah, so now there's, and therefore correspondingly you need to, I mean, in the sigma v versus m plot, you need a much larger cross section. So there's just one problem with this argument, and that is that these particles, the S particles, now come with a very large abundance. Yeah, and of course, that is not cosmologically viable. You would basically overclose the universe. So you have to get rid of them. And then there are, from a model building point of view, just 2 options. So one is that you have some kind of late time decay with very weak couplings that don't affect the freeze out process, which means that you inject entropy in the dark sector, therefore dilute everything. Or you have like a small residual coupling to the standard model, and in this way rethermalize the energy that is stored in the S particles. And these 2 options are shown here. So the solid lines are always the case where the entropy injection is just into the standard, into the dark sector. So then you see that you need a much larger annihilation cross section in order to get the correct relic density. compared to the standard case where you have vanishing chemical potential, as I've showed you before. So this is basically to bring this line down here again. And then the dash dotted lines show the case where the decay is into the standard model heat bath. Okay, so let me maybe very briefly mention just yet another possibility of how the dark matter particles could decouple from the heat bath in a way that is different from the standard situation. Yeah, so we said before that a basic assumption is that we're always in kinetic equilibrium, and everything that I've shown you so far assumes that there's perfect kinetic equilibrium during the freeze-out process, independently of whether the annihilation products build up chemical potential or not. Yeah, now, this, I mean, the decoupling of the scattering processes can also be described by referring to the Boltzmann equation. Yeah, so it's just that rather than integrating over the Boltzmann equation, so considering the zeroth moment, which is just the equation for the number density, one can consider the second moment. Yeah, so you multiply it with p squared, the momentum squared, and then integrate over the momentum, which results in a differential equation not for the number density, but for the velocity dispersion, which you can relate to the temperature in equilibrium. So you can introduce this basically as a definition of a temperature, you can call it parameter, that describes the deviation from equilibrium, from kinetic equilibrium. Yeah, and then you can solve this equation, the resulting differential equation, and see that as expected at early times, yeah, the evolution follows very closely the or is exactly the same as the background temperature, while at late times there's just redshift. Yeah, so it as expected, it goes, the temperature drops like the scale factor to the -2, and then the point is that this transition happens very fast, which allows you to really define the time of kinetic decoupling. Okay, so what happens if this assumption is not satisfied anymore? If for whatever reason, in whatever model, annihilation and scattering happen on similar timescales, then there are basically two options. We can try to solve the underlying Boltzmann equation at the phase space level, which is of course numerically challenging. And in particular, it's challenging to add another process, which I haven't mentioned here yet, and that is dark matter self-scattering. Yeah. So this is complicated because here, for this process, you can use the fact that we have non-relativistic particles scattering on relativistic particles. So you know that the momentum transfer is already always small compared to the temperature. And that is something that you can use in order to expand the collision term. That makes the treatment easier. If you have dark matter scattering, this is no longer true. Yeah, the momentum transfer is large, and that means the analytical and also the numerical treatment of the collision term is much, much harder. So the second option is to truncate basically the Boltzmann hierarchy at the second moment. Yeah, so by assuming that we are that the dark matter particles equilibrize with themselves, so basically assuming that we have a very efficient self-scattering. So that is of course much easier to treat numerically, and well, in the limit where this is very efficient, it's even the exact treatment. Okay, so the first application of such a coupled system of Boltzmann equation was for rather late kinetic decoupling and the situation where the annihilation is Sommerfeld enhanced. So that leads to a second period of annihilation, because after kinetic decoupling, the dark matter temperature drops like the scale factor to the -2. So dark matter, in other words, becomes very cold. And then you know that for Sommerfeld annihilation, the annihilation rate scales like 1 over the relative velocity, or on parametric resonances, even like 1 over the velocity squared, which means that long after the standard freeze out, dark matter particles can start to re-annihilate again. We have studied this recently, sort of and updating the description, and the full set of equations that are necessary to describe this are given here. So it's basically an equation for the number density and an equation for this temperature parameter, so the velocity dispersion. So the things that enter here is, I mean, this is just the standard equation, just rewritten in, so the standard equation for the dark matter number density rewritten in terms of this dimensionless abundance. So the only change here is that rather than considering the thermal average of dark matter annihilations, you should consider the thermal average with respect to a dark matter distribution that takes into account that it may not be the same as the heat bath that you're annihilating into. So in other words, you should self-consistently follow the dark matter phase space, or the phase space distribution, the momentum distribution in computing the annihilation term, while for the production term, where you're using the heat bath temperature. Then for the dark matter temperature, this here is just the standard term that describes kinetic decoupling. So this is the momentum transfer rate. And then there are two additional terms that describe how dark matter is heated or cooled by annihilation. This is this part here. So basically, if annihilation is momentum or velocity sensitive, then you can, like if you predominantly annihilate for a very small velocity, as in the case of Sommerfeld enhancement, then this will mean that you deplete your phase space from small velocities, small momenta, and therefore effectively increase the velocity dispersion. This is described by this term. And then correspondingly, this term describes how the dark matter velocity dispersion changes due to the creation processes. And then there's just a small correction term that is only relevant if we have relatively early kinetic decoupling. So an application, and this is my last slide also, is the scalar singlet model, which you can argue is the simplest and therefore nicest wind model that you could think of. And in particular, the like close to dark matter masses, so scalar singlet masses, roughly half of the Higgs mass. The dominant process here is just via the standard model Higgs and in an S channel. And this shows you here sort of a zoom in on that region from a recent global scan. And you see that, as expected, the coupling that you need between the scalar singlets and the standard model Higgs, so this is this coupling here. This can be very, very small on the resonance because the process is resonantly enhanced. So that means you get the correct relic density for a small coupling. But then, of course, the point is that if you have a small coupling here, then if you rotate this diagram by 90 degrees, then it means that the scattering process that keeps the scalar singlets in thermal equilibrium with the standard model particles is also highly suppressed. So this is a prime example of where, in general, actually on resonances, where this assumption of kinetic equilibrium during freeze-out fails. And we just implemented the set of equations shown on the previous slide. And what we show here is the ratio of the relic density that you get in the full approach divided by the relic density that you get with the standard treatment. And you can see that, so this is the parameter region close to the resonance. And the difference can be like a factor of a few, which you should compare to the percent level precision to which you measure the relic density. So this can be a very important effect, generally close to a resonance. So let me just mention that there's now an implementation in DarkSUSY, which of these coupled Boltzmann equations. And you should really think of this as the correct description of the system, assuming that in this model, for example, this coupling here is large. So if you have sufficient self-interaction such that the thermal averages that enter the equations are described to a good accuracy by assuming that we have a thermal distribution, assuming a free temperature parameter. And there's another code that we are about to release that actually solves the full Boltzmann equation additionally at the phase space level. Yeah, so this means that this will give the correct description, also as indicated here by the dotted lines, for the case where we don't have any self-interactions, so where we, strictly speaking, just set this term to 0, because as I mentioned before, the implementation of dark matter scatterings is numerically very challenging. So this is something we cannot do yet. Okay, so this brings me to my conclusions. So in general, I think like dark sector models are very interesting. And of course, there has been a lot of interest recently, not the least because they are actually testable and they are very predictive. And the fact that these are so predictive is directly tied to the observation that we can compute the relic density to a high precision. And I think this is a very good argument to aim for freeze-out calculations in these scenarios with a high precision that is standard by now in standard model calculations, but not in dark sector calculations. And well, finally, I hope I made the point that this is a tool that is definitely not restricted to supersymmetric models, but that is quite, I mean, versatile, that you can use to study these kind of dark sector models. Okay, thanks for your attention.
Thank you very much. Is there any question or comment in the audience?
In this case, with the chemical potential for the scalar, where it's massive, you say you could have entropy production to dilute it away, but then this would also dilute away the dark matter, right? So,
sure.
So in the end, your dark matter is essentially a mixture of the scalar and the chi particle.
No, I mean, the dilution works in such a way that the scalar just completely goes away. So it decays. I mean, the idea is that it decays into relativistic particles, yeah, which would contribute to delta and F. But if the decay or the conversion happens early enough, I mean, this is basically the constraint, that you have to make sure that this conversion happens so early that delta and F is not too large to be in conflict with BBN. Yeah, but in that case, you just have a small contribution to delta and F, which even could turn out to be a signal. And then, as you say correctly, also the dark matter density is, of course, diluted. And in the plots that I've shown you, this part is taken into account.
Okay, thanks.
Yeah, otherwise you would need like even larger annihilation rates to bring the required abundance down to the observed level.
So other questions or comment?
So thank you for very nice explanations with your work. And so you are now advertising DarkSUSY. I mean, so you can do more general model as case. And then, so I think that in the older versions, we have to provide matrix elemental scalar as an input, right?
Yeah. Okay. So this is
correctly. But now, do you have some simpler way to do? I mean, defining the model for DarkSUSY. Do you have some backup slide? Yeah.
Yeah. No, I just want to get back to the overview slide. So, okay, good. So, I mean, this is the one part that we basically don't focus on in DarkSUSY. Yeah? So, like for the step going from a model Lagrangian to an annihilation rate, yeah, this is, I mean, there are many tools that do this already automatically.
Right.
For example, CalCap. Sorry. Okay. So, for example, CalCap. So the philosophy of DarkSUSY is slightly different. Yeah. So here we try to basically maximize the precision and effectiveness of this core library, the main DarkSUSY library, in order to have a relic density calculator that is as model independent but still as precise as possible. Yeah, so that means that we basically connect this to a given particle model by means of so-called interface function, and we try to minimize these interface functions. So for the case of relic density calculation, the only thing that is needed is the invariant annihilation rate. Yeah, and the code basically does not care how you provide the invariant annihilation rate. So this could even be a table that you get from somewhere else.
Let's see.
So in that sense, like the models that we provide here are more like example implementations. Yeah, so typically, like, okay, for example, there is a simple dark sector model close to what I just showed you implemented. Yeah, so there it would be very simple to change, for example, degrees of freedom, or also to change the matrix element. But still, these are external inputs, so you would have to change these things.
And compared with the micro omegas, so you in DarkSUSY in the current version also produce delta and effective and other observables relevant for cosmological tests.
Yeah, so I think, but I mean, don't take my word for this for the most recent version of Micromegas.
Okay.
But I think none of these things that I highlighted in red are currently included in Micromegas. Yeah, so you cannot really track temperatures different from the standard model temperature. Yeah, and in particular not like fully automatically self-consistently. So in DarkSUSY now, if you have specified your model in terms of particle content, this is automatically calculated and always kept self-consistently. And then there are self-interactions, the delta and F that you get as a function of temperature, and so on.
Thank you. Are you, by the way, are you planning to also include the simple scenario? Strong inter. So
yeah, I mean,
3 to 2, 4 to 2, etc.
Yes, so planning 2 is a good way to put this, right? I mean, it's certainly on the to-do list, but the to-do list is long.
Please.
Yeah, so the next thing that will come is what I mentioned, these coupled Boltzmann equations, where you have basically freeze out of equilibrium and can describe, for example, early kinetic decoupling that you have, I mean, generically in the presence of narrow resonances, but also late kinetic decoupling interfering with Sommerfeld enhancement.
Yes.
So this is this should be public relatively soon.
A somewhat embarrassing question. In your modified Steigman plot for, I think, this massless scalar model, there are these curves for the standard model. What do these actually mean? It's not the dark matter density in the standard model, right?
Yeah, you mean?
Yes, right.
Ah, no, I mean, no, this is the standard case. So if annihilation is 2 standard model heat bath particles.
Ah, that was it. Okay.
So these are really, yes. So these are really the standard. This is the standard Steigman plot, the orange one. So this is exactly the same, just for comparison.
Okay, fair enough.
Yeah, and I mean, I said that, like, of course, you can say that this is kind of obvious, but still, I mean, we learned from looking at the literature that typically not all of these effects are self-consistently taken into account. And I don't want to add here a shame and blame list, but I can use my own example. So this plot here, yeah, is a plot that is also included in the DarkSUSY paper. And there, indeed, we also missed one of the effects. Yeah, so you see, like, if you compare this carefully to the plot in the DarkSUSY paper, yeah, you see a small change of these curves, like order 1 change of how the couplings are set. Yeah, so this is just one example of where now it is like all implemented fully self-consistently. But in concrete models, in concrete relic density calculations, it happens relatively often that people just neglect one of these things or forget about one of these things. So this is another motivation for this work, essentially, to just have sort of a simple cookbook, if you wish, of what you have to do if you do dark sector calculations, relic density calculations.
Okay, is there any more questions? Okay, if not, let's thanks to Torsten again.
Okay.
Thank you very much for a nice
Very
talk.
much. Thank you.
Thank you.
Thank you.
Hope to see you around soon.
Yeah, I hope so too. We all hope to be able to travel again, right?
Okay, bye-bye.
Okay, bye.
Could you please send your talk file to email?
Yes, I would.
Yeah.
Yeah.
Really?